Okay, another major announcement, boys. This blew my mind. I stumbled across it on a robotics forum, and it blew my mind. I gotta share this. So, as you guys know, when you're like bending a finger for the robot, you need to be able to measure, like, is the finger like this or is it like this? Like, you need to know with some degree of precision about what it is so the robot knows what its body is looking like. So when it's modeling, like, frame by frame, its grasping motion, it's predicting how it's going to be moving itself. It will know where it's at and where it needs to be, and it will be able to like know what progress it's making on whatever motion it's intending to do to carry out some action. And so it needs to know those joint angles. Now, Will Cogley on YouTube uses potentiometers to measure joint angles, and that's what I've been planning to do for years. And a lot of other people do that. But someone on a robot forum mentioned using linear Hall effect sensors to measure joint angle. And I was like, oh, I kind of have some vague idea of what that's all about for like wheel speed sensors on a vehicle. And some brushless DC motors have Hall effect sensors built into them. That means more wires coming off the motor makes it a little more expensive, and that gives you some feedback as to the progress of the rotations of the motor. But it's not really necessary since sensorless motors control is possible by being able to read the back EMF of the rotating magnetic fields using a voltage divider circuit. You can sense that the motor's turning that way by the back EMF it gives off, and that can be read in through the analog input pins of your microcontroller, and it can know what's going on with that. So you don't really need Hall effect sensors built into motors per se. So I knew kind of those things about it, but I didn't know that much. And it turns out a linear Hall effect sensor. I don't know about all of them. I haven't researched this a lot, but I know enough. A linear Hall effect sensor. Apparently, its voltage output. It has three wires: 5 volts in and ground, and then another one is your analog reading pin. It's a linear Hall effect sensor. It's a little tiny IC chip with 3 pins. And as magnet goes near it, the voltage it sends back to your microcontroller analog input pin is a bigger voltage. As the magnet gets further from it, that voltage gets smaller. And so if you stuck a Hall effect sensor here and a magnet here, as the finger bends, the voltage would increase. As the finger extends, the voltage would decrease, and you could calculate the angle based on mapping that and measuring it. You'd be able to know what angle the finger is. You can buy a Hall effect sensor IC chip in a very small surface mount package that would be able to fit on the finger. And then you can buy a very tiny neodymium magnet that would fit on the finger, and it would be able to measure the distance of that magnet from the sensor and thereby calculate the angle of the joint. And this would just be 3 tiny little wires that's needed: 5 volt ground and your analog wire to be able to read what that Hall effect sensor is giving off in tiny, tiny neodymium magnets. So this is what I bought, and this is theoretical so far. I haven't seen anybody talk about this or do this, but I just saw it mentioned. I looked into it and talked to ChatGPT about it a good amount. So I bought 1 millimeter thickness, 3 millimeters diameter neodymium magnets, 150 of them for $8 on AliExpress. So they're tiny, tiny, 1 millimeter thickness, 3 millimeters diameter, tiny little disc magnets that I could put on the robot's finger, and then the IC chip would be right next to it, the linear Hall effect sensor. I bought linear Hall effect sensor 49E SOT23 package times 100 for $11 on AliExpress. And I'll show you guys a picture of a Hall effect sensor like that. It's basically super, super tiny. And I mean, these things are, I think it's only like 3 millimeters by like 1.5 millimeters. So tiny, tiny, tiny. And then the height might only be like 0.4 millimeters height. So that's real small. And that's it, the 3-pin Hall effect sensor. That's how it looks. Boom. And so that's what I'll be trying to use now instead of potentiometers. A potentiometer, I was going to take a potentiometer, like the dial kind that has a turn dial, and I was going to have to make like a little pulley system and then have string coming from the finger wrapping around it in different directions. So when the finger extends, it turns that dial, and when it contracts, it turns it the other way. And so then that thing would be spinning in relation to the finger joint, and the little strings would be affected and pulled as the finger moves. And setting up, running the strings and the tubing for the strings, and creating a tiny little pulley on top of customizing that little potentiometer like that. That's a lot of precision, manual labor, very skilled labor with good magnification and a lot of planning, and takes up a decent amount of space. Even though it is a little bit tiny, it's nothing compared to how tiny this is. So this Hall effect sensing of the joint angle of the robotic joints appears to be a superior approach. Another alternative, if I need to, for certain joints, if I had to, like maybe the elbow joint is just traveling too far, the Hall effect sensor would not be able to sense the magnet very well or something. I could use a bigger magnet in that case, or potentially I could have a little magnet and a little Hall effect sensor that are just facing each other, and then a string does still go out to the joint, and that string is set up to pull the magnet this way and a track, and then when the joint moves the other way, a string that wraps around a dowel pin and then comes back to it and pulls it back on a track. So I could have the magnet move back and forth on a linear basis on a very small scale. I could even down gear the string to have the linear motion reduced or increased as needed to where the magnet goes the optimal amount away from the Hall effect sensor back and forth to measure the angle accurately, and the translation of the rotation of the joints being communicated by way of strings to this little, basically it'd be like a linear sensor, custom sensor system that measures linear distance within a certain linear range of distance using just a chip and a magnet on a track, like a rail track. And as the distance changes, the mapping of like when the distance is this much, the joint is at this angle. When the distance is at this much, the joint is at this angle. You'd be able to figure that out and calculate that with an algorithm in the software and know the joint angle based upon those voltage readings that are mapped to distances. And so in this way, you'd be able to know the joint angle. And so I will most likely not be using potentiometers anymore. And I got criticized for my plans to use potentiometers. People said that they don't last long, they're not accurate enough, blah, blah, blah. I think they're fine for this, but this is smaller. And probably about the same price. I mean, well, potentiometers might be a little more expensive. So this is, but the labor involved is much less, especially because this is just a few wires and a magnet. And I don't have to create like little pulleys and stuff on on a potentiometer.